Okay, so welcome to my uh, yapping of science and math. So first off, we'll be talking about projectile motion. This one's pretty standard, but anyways, bear with me. Okay, so projectile motion is what happens when, say, you throw something like a ball. So, oh, that's a bad drawing. Uh, Picture a man, and then he throws something. So whenever whenever we throw something, it will always have what we call as an initial velocity. An initial velocity. Now velocity is a vector. We all must remember that it has a magnitude and direction. Okay, so about its direction, um, we determine that using the horizontal line. This horizontal line right here. Let me, well, whatever. Okay, so uh, now we we measure that angle, and that is the angle that we need throughout our calculations. Since physics is is an applied subject, we shouldn't worry too much with the theory here. So yeah, that's about it. Well, when you have an initial velocity like this, it this ball or whatever object it is will travel in a parabola looking uh, trajectory until uh, until it lands here or wherever this ground is. But typically, we just picture it as a ground. So let's picture it as ground. Uh, let's let's make that green for uh, realistic purposes. There. Okay. So yeah, the ball will eventually land there. Okay. So what we have now is uh, the angle theta and the initial velocity vector. But the thing is, unlike free fall, unlike free fall, which just free fall, it just relies on one direction, which is y, the y direction, and the acceleration here is the force of gravity, which is 9.8 meter per second square. And in commonly we use the negative. So in that case, we will refer to the full vector definition of the acceleration. So that's it. So that's free fall. The problem with projectile motion is that we can't operate on two dimensions at once. So we have to break this into components. So the way we do that is we use trigonometry. Okay, so uh, here we have, let's choose this. Here we have, for the x direction, we have your v naught, or initial velocity, cosine of theta. And the for y, we have v naught sine theta. And that's about it. This is the initial velocity for the y direction, and this is for the x direction. Okay, so okay, so since projectile motion and free fall motion both occur on Earth, okay, uh, only the y direction feels the force of gravity, and therefore uh, the acceleration, to put this into words, uh, so we have 2 points here. So first point is the acceleration in the y direction, ay, is uh, negative 9.8 meter per second square. And the second point is that the acceleration for the x direction is 0 meter per second square. So that's it. We don't have any acceleration in the x direction because it does not exist physically. Okay, so now how do we derive our formulas here from here on? Okay, so well, what do we do? uh we first have to take into account that uh these two are independent. Okay, they are independent, uh so they don't affect each other, and so we can work on them separately. So we first look at the x direction first. Okay, so let us do our analysis on the x direction first. Since since the acceleration here is just 0, this means that the velocity is constant. Okay, since the derivative of a constant is 0, and the derivative of velocity is acceleration, then velocity is constant. Okay, but what is that constant? So it means that Vx throughout the motion is constant, and the only value that uh, makes sense for this is v naught x, or this one. This is v naught x. This is v naught x. Okay, it's the initial velocity. Oh no, it's the x component of the initial velocity. So that is v naught cosine theta. So what this means is that the uh, the x velocity throughout the whole motion is just the x component of the initial velocity. Okay, so I hope that makes sense. Okay, now how about the uh, position? Well, since uh, since position, the position function x of t is nothing but the integral of the velocity function with respect to time, okay, from v naught to v. So what we have here is the constant v naught cosine theta dt, and that's from, oh, no, no, yeah, I think so. Is my bounds correct? Hmm. Yeah, I think so. We'll see. So integrating a constant gives itself times time, unit cosine theta times time, and then that's v naught and v. So yeah, that's just v naught cosine theta. Oh wow, v minus v naught. So that's it. Yeah. So that's x of t. X of t. Oh, I was not supposed to make this an indefinite integral. Oh, I was not supposed to make this a definite integral. My bad. Since we were looking for the function of time of the position, I am deeply sorry about that. Uh, okay. So let's just do the regular antiderivative. So that's v naught cosine theta dt, and yeah, that just gives us v naught cosine theta times time plus c. Okay, but okay, so that is x of t. Well, what is c? C is x of 0. Okay, x of 0 is just c. Since this cancels out, this makes anything 0, so we're only left with, well, 0 plus c. And I hope that makes us that makes it clear uh, that makes it clear that x of 0 is just c. So x of 0 or x naught is c. So meaning we have x of t equals x naught plus v naught cosine theta times t as our position function for the for the uh x direction. Okay, so we have three key formulas for the x direction. Hmm, I just blue this blue. So uh this one for the velocity, and this one for the uh position function. Now these are all time dependent. Okay, they all they all depend on time. They use time as the variable. So yeah, uh but aren't you curious if okay, but acceleration is zero for the x, so doesn't really matter if we don't depend on time. But here it will matter more in the y direction. Okay, so in the oh, that's too near. So in the y direction, the ace of y is negative g. That's the abbreviation we commonly use to not write 9.8 meter per second square every time. So yeah, it is negative 9.8 meter per second square. And this is just the abbreviation we use. Okay, so since we have uh, uh, a value here for the acceleration, but it's just a constant. What is the velocity? So the velocity Vy is the integral of that ay dt with respect to time. So what we do is we integrate negative g dt. Okay, so we get negative g t plus c. Okay, so that's our Vy right there. Vy of t. Plug in 0, we get Vy of 0 or V naught y. V naught y. You can just do it like this, right? V naught y. It's ugly right there. It's so ugly. V naught y. That is just 0 plus c. But what is c? This V naught y actually is what? It's the it's the y component of the of the initial velocity vector. Okay, so from our uh, illustration earlier, that is v naught sine theta. So this is v naught y. The initial, no, the y direction, no, the y component of the initial velocity vector. Okay, so that's that. So that's that. Uh, so that is v naught sine theta. So that's the v naught y. Yeah. So we plug that back in. So our full, so our full, uh, so our full expression for the uh, velocity in y is negative gt plus v naught sine theta. Okay, so that's that. That is the uh, velocity in the y direction of a projectile motion. Okay, so I hope you're getting this down. So since we have an acceleration here as a constant, the as a result of integration with respect to time, our velocity is not a constant. Okay, so that's that. So that's that. Uh, Next is the position vector of our position function with respect to time of our y. This is the most important part actually for me. Okay, so no, that's not that. So y of t is the integral of the velocity function with respect to time. Uh, if, with respect to y, yeah, the y of vy of t. Yeah, this is understood to be a function of time. I just didn't write it. Okay. Uh, for those of you who may be wondering why is the position the integral of the velocity, here's why it is the case. So we define we define the velocity as the derivative of the position function with respect to time. And so by separating variables v dt, vt dt is what uh, v x of t. And if we integrate that with respect to time for this one and then this one, uh, we get x of t, or the position function is just the integral of the velocity function. Okay, so it's a very good side note there, and 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 it also works for the acceleration. The velocity, no, the acceleration function a of t is the derivative of the, no, of the velocity function with respect to time. And if you work out the same math, we just get uh, v of t is nothing but the integral of the acceleration function. Okay, so that's where I got my formulas back here. Okay, so back to the position function for the y direction. So we are just gonna integrate vy of t, and vy of t is this one, negative gt plus v naught sine theta dt. Okay, so working out the math, we get negative g over 2 t squared plus v naught sine theta times t plus c as the constant of integration, and that is y of t. And if we set t equals 0, okay, we get y of 0 is just what, c, or the initial position. So this is the initial position. Okay. Uh yeah. So the full um position function in the y direction, as you all may be familiar with now, is just uh, y naught plus v naught sine theta t minus g over 2 t square. And this is our position function for the y direction. So yeah, that's very important. So we all now have uh, our time dependent. These are all our time dependent formulas for the motion in the y direction of our projectile motion. Okay, so these are the formulas to remember. So yeah, but what if what if time isn't given? Like, we how about if you only have acceleration, position, and then velocity, whatever that is. If we have, if we don't, if we are not provided with time, so how do we work around with that? Okay, so how do we do that? Okay, so the way we do that is we go back to this specific detail right here. The acceleration vector. Uh, oh, that's why do I have that here? Okay, so the acceleration vector is the derivative of the velocity vector. So what if we could just do it with um, tricks, mathematical tricks, and I'm not gonna pull up a of t anytime every time. I'm just gonna write it as a equals dv by dt. Okay, so I think that sounds better. That looks better. Okay, but here we don't want a time in. We want to be time independent. But how do we do that? Okay, okay. So we use chain rule. So we just uh, do this. Well, we keep no. We will use the fact that it is equal to dv by dx over dx by dt. Okay. By the chain rule, this is given by the chain rule of differentiation. This is guaranteed to be true. Okay. And now there we have it. We can we can be now time independent because look at this. What is dx by dt? Dx by dt is nothing but the velocity vector. So in other words, a is nothing but v times dv by dx. Okay? And assuming for our purposes that a is constant, uh, well, for our purposes for projectile motion, we can separate variables. So we can move dx here and then just leave v and dv here and then integrate. So integrate that. So a uh no we will integrate this from x naught, from the initial position to the final position, and then from the initial velocity to the final velocity. Yeah, that sounds about right. Okay, so now we have a times x minus x naught equals, well, what is the antiderivative of v? That's v squared over 2. And let's evaluate it from v naught to v, the final velocity. Okay, so what is x naught? That is the change in x, delta x. And this one, uh, well, since 2 is a common factor here, 1/2 is common factor here, we can just move it here. Get 2 a delta x, and then we get here v squared minus v naught squared. And rearranging, we have here v v naught of v squared is v naught squared plus 2a delta x. So now that is our very familiar formula right there. This is my MVP for kinematics. Okay, so this works when you are not uh, given information about time. So these are the formulas that I really cling to whenever I'm dealing with projectile motion. So yeah. So Next time, we'll talk about the applications of these uh, formulas, and we'll move further into more specific problems in projectile motion, such as the maximum height, the range, the whatever else is there. So that's it. So that's it. Goodbye. This has been Euler Phil. Thank you.